All right, hello everyone. I am sharing my screen because I'm now recording. I wasn't a second ago. Okay, so listen, acid-base chemistry is tough. In my opinion, it's one of the hardest things that we have to learn, and I'm doing my absolute best to try and make it as straightforward as possible, okay? So we're going back to 8.4, so we're going to do 8.4 and 8.6. And then we'll go and do 8.8, 8.9, and 8.10, okay? So we're going to talk about acids, acid-base reactions, and buffers. And then we're going to do some practice. There was a practice problem in the middle, and then one at the end. And I'm going to try and give you sort of an overview of how to approach different problems, because that's one of the big issues with acid-base chemistry is students get really frustrated because there's so many different ways to solve them, and you can't use all the methods. It depends on the scenario, and so the scenarios are really important. And so I'm going to try and break that down for you in sort of like a little data table that we can start to try and compartmentalize and figure out how to solve each problem. All right, so let's get into it. So we can have a strong acid, strong base neutralization. So when that's happening, like hydrochloric acid and sodium hydroxide are the most popular, you're going to see a lot. And what we end up with is an acid plus base. So this is my base plus my acid. It gives me a salt plus water. So the net ionic equation for this, because I have sodium, who is always soluble no matter what, and the chloride is soluble unless it's in the presence of one of the heavy metal bad dudes, which are silver, mercury, and lead, not happening here. That leaves me with this net ionic equation where my H plus my OH minus is going to give me water. And most of the water molecules are going to stay intact. There will be a few that self-ionize, but for the most part, you know, H2O will stay together. All right. Now, strong acid, strong base neutralization. We have discussed this already. So at the equivalence point, which is right here, which is where our moles of acid equal our moles of base. This is going to happen at a pH of 7 for a strong acid, strong base neutralization. Okay. Why? Well, because we have a neutral salt. Okay, so that's the main thing. We have no acid, no base, because they are in the form of water. Now, for this particular one, this is a strong acid, strong base neutralization. I can tell by looking at the graph that it's a strong acid. Why? Well, the pH is 1. Notice it doesn't have that initial jump in pH. It's just sort of pretty level the whole time. As the pH is changing, as the titration is going on. The equivalence point is 7. And that's where our moles of acid equal our moles of base. So for strong acid-base neutralization reactions, we use stoichiometry to solve. So this is where we're going to get off. I'm going to go off on a little tangent for a second. So find somewhere to take good notes on this. I was literally just thinking about this right before I started the video. I was like, I've got to figure out a way to make this make sense. So I haven't actually created a data table, which I probably need to, but for right now, I'm just gonna write some notes on it, okay? So if what I'm having, and W is weak. Because if you're dealing with strong and weak, it doesn't matter if it's an acid or a base. The point is, if you're dealing with something strong, 2 strong things, 2 weak things, or strong and a weak. That's where it determines how you solve the problem. So I'm not using an A or B for acid or base because that's irrelevant. All right, so if I'm dealing with a strong reaction, so it's a strong acid, strong base, then I use stoichiometry. But in one of the other videos that I made, the stoichiometry is sort of long and it's tedious. What you can do, the calculation that you can do is M1V1 equals M2V2. And I'm going to put an asterisk on there. Just make sure you check the stoich. Because, for example, if your base is like calcium hydroxide, we have 2 hydroxides for every 1 H plus that's coming off of your strong acid, then you need to be aware of that because that's going to change your answer a little bit, and you need to go back and adjust your mole to mole ratios. And so that is here. So that's usually pretty easy. Most students don't have too much difficulty with that one. That one's pretty straightforward. And we've been doing some of these other ones, but we really just need to like make a list, and this will be a reference spot for you to come back and check what to do in a situation, like how to solve it. So let's see. If I have strong weak, and I'm going to have several of these because there's several possible scenarios. So if I have strong weak where I have excess of the strong. And so when I'm talking about excess of the strong, you need to take it down to the moles. All right, so strong and weak, and I have extra of the strong, then that one's also pretty easy to solve. You're gonna find your moles of acid and moles of base. And when you do that, you will just subtract them, and you will equal the moles of excess strong. And then once you have the moles of the excess strong, we're going to do one of these in just a minute, so don't get too upset if you're not following. Then once you have the moles, then you'll go to the molarity, and then you can go to the pH from there. Okay. So if you have excess of the strong, you got to get the moles of everything. H plus OH minus, that's in a 1-to-1 ratio. It'll give you your water. And so if you have whoever's strong, it doesn't matter if it's the acid or the base, whoever's strong that's left over, that number of moles is what is going to be creating or contributing to your pH, okay? Now, if we have a strong weak and the excess is the weak, so if you think about the graphs, you are in the buffer region. Yes, you also need the moles to know for sure. So you need to do the mole calculation real quick to find out which one you have more or less of. Is it more of the strong or is it more of the weak? Okay, so if you still have excess of whoever's weak, then you're in that buffer region. So you're in that part of the graph, remember I told you, in the weak you have a quick change in pH and then it levels out, okay, before it gets to that inflection point. So you're in that leveled out range. You haven't gotten to the inflection point yet if you still have extra of the weak, unless you have the weak in the burette. And so, and it would be the opposite. But here's the point, is if you have excess weak, regardless of who is where in the flask or the burette, it doesn't matter. If you have excess weak, then since you're in the buffer region, then that's going to be the Henderson-Hasselbalch. I'll just abbreviate that. And so we're going to be in the Henderson-Hasselbalch, which is going to be your pH equals your pKa plus the log of your conjugate over your acid. All right, so this is your way you're going to solve this. All right, now is there another one? Of course there's another one. Of course. Don't be silly. Of course there's another one. What do we do if we have the strong, weak, and there is no excess? And when I'm saying no excess, I'm referring to there's no H plus or OH minus. This has a special name. It's called equimolar. Okay, so it does mean it has the same, equi means equal, so the same molar, like molarity, but it's specifically talking about the moles. So it has to be the same molarity and the same volume, same molarity, same volume, as the same number of moles. So if you were to subtract the moles of the acid and the moles of the base from each other to find out how many moles are in excess and your number is 0, then it's a different type of problem. Then you're dealing with a rice table. So this takes it pretty much all the way back to Unit 7. Okay? Now, of course, there's weak, and this one doesn't pop up that often, but when you have weak, what you're going to do is you have to look at your Ka and Kb values. And I'll just leave that one alone because we're not going to work on that one right now. All right, so today where we're going to spend our time is, well, we got a little bit of this one, and then we have these. I'm going to work a couple of problems in this range here for sure, because those are very common on the AP exam. They throw kids for a loop because they don't know what to do. They don't know how to solve the problem. So what I want you to do when you have a strong weak is, first things first, just go solve for the moles. Okay? So when you're having a strong weak situation right here, so what I want you to do is go solve for moles. And then determine what's the excess. And as soon as you know who's in excess, is it my strong that's in excess? Then I got to deal with this. If it's the weak that's in excess, then I need to do this. If there is no excess, then I got to do this. So that's where I want you to think. That's where your brain needs to be whenever you see these problems. They are daunting and they're kind of scary, but don't let them scare you. We got this. You can do it. All right. So this is really it. I'm not going to spend a bunch of time on the strong acid, strong base, because we've already talked about it. But the equivalence point's at 7. If you have a weak, somebody weak in there, then the equivalence point is not going to be at 7. The only way that the equivalence point would be at 7 for a weak reaction is if it were a weak, so weak acid, weak base, and they both had the same value for their Ka and their Kb. So this does happen with acetic acid and ammonia. Okay, so acetic acid and ammonia, acetic acid has a Ka value of 1.8 times 10 to the negative 5. Ammonia has a Kb value of 1.8 times 10 to the negative 5. And so they do create a neutral salt. And so their pH at their equivalence point will be 7. But other than that, of course, I'm sure there are others where they have the same Ka and Kb value, but they don't pop up that often in AP Chem. So we're not going to stress and worry about that too much. Okay, so with strong. So for this particular example, we have 25 mils of a sample of HI requires 46.23 mils of 0.203 molar, 0.203 molar NaOH. I don't know if that's typo or what, but that's okay, it doesn't matter. We got it. Solution to reach the equivalence point, calculate the concentration of the HI. All right, well, it gives you some steps right here, but I'm not going to do the stoichiometry method because this is taking me through like the stoichiometry method that I need to do, because I'm like, no, dude, I'm just going to do M1V1 equals M2V2 because it's just so much easier. This H donates 1 proton. This is OH minus is 1-to-1 mole-to-mole ratios. I don't have to deal with any problems related to that. So I have my V1 here, I have my V2 here, and I have my M1. So, oops, M2, my bad. All right, so the molarity of my acid times the volume is 25 milliliters. I don't need to convert it because I'll have milliliters on both sides, so the units will cancel out. And then I have 46.23 milliliters times 0.203 molar NaOH. I have no idea what this equals because I haven't worked this problem recently anyway. All right, divided by 25. All right, so I do my algebra. Hopefully I did it right. Molarity for my acid, I get 0.3. Let's check our sig figs. 3 here, 4 here, 3 here, so 3 sig figs. 375 molar HI. Okay. Now hopefully that makes perfect sense. Why would that make perfect sense, you ask? I'm so glad you asked. Well, because this is 25 mils and this is 46 mils. So it took more of the base to neutralize that acid. So if it takes more base to neutralize the acid, then the acid should have been stronger. And 0.375 molar is stronger than 0.203 molar. Okay, so that's a strong. We're not going to spend much time on that because that's pretty easy. Okay, so now calculations from what we've previously done are a lot easier when things ionize 100%. So that's the strong. So now when we're dealing with weak, that's when we kind of start to get into some bumps in the road. That's why it's a little bit harder to try and figure it out. So let's say we have a weak acid like acetic acid, and then we have the strong base, which is NaOH. And they're going to react, and you see this equation that we have here, and then yes, it's at equilibrium because I have a weak acid involved. Now, one thing I do want to remind you of that we haven't talked about yet, that if I have a strong acid, then it has a weak conjugate base. I don't think I can write up above, so I'll write over here. And a strong base has a weak conjugate acid. So we've talked about this previously. I'm not quite sure which section we discussed this in, but this is important for you to kind of get a grasp on what's going on. And then opposite of that is true. If I have a weak acid, that means it has a strong conjugate base. And if I have a weak base, then it has a strong conjugate acid. So that's going to be important, maybe more conceptually than anything else, for you to understand what's happening when we're doing our reactions in just a minute. All right, so for this NaOH and acetic acid reaction, my salt is the sodium acetate, and then I have water. All right, so when you go through and you get rid of everything that is gonna not react or do anything, get the net ionic equation, the sodium is out, and then really that's all that's out. So I have my acetic acid is the acid, the HA, and then I have acetate. Acetate is going to be floating around doing stuff, so he's my conjugate. All right, so he's going to be floating around, but he's going to maybe do some stuff. So we're going to leave him in there, and then I have water, and then so on and so forth. Why do I leave him in there? Because if he interacts with an H+, where's an H+ going to come from? Well, remember, water will auto-ionize a little bit, and so there could be an H+ floating around. And since this is a weak acid, that means this is a strong conjugate base. So if there's an H+ floating around, it will react and go back and create more of the acetic acid. So that's why the acetate needs to stay in. Typically, if you're just dealing with a salt, then acetate is always going to be soluble, so you cancel it out like sodium. But because there's H+ floating around in the solution, it actually can create the acetic acid, so it has to stay. All right, so now let's take a look at this one. So this is a titration, and it tells you at the top, but hopefully you notice right away, this is a weak acid. Why? Because the starting pH is above 2. It's got that initial curve, and then it buffers out. Our ending pH is a little above 12, so that's going to make this a strong base. And our equivalence point is above 7, so that makes perfect sense. All right, so you can, when you set the best way to do a titration is to have like a pH meter or an electrode, sometimes they're called, but a device that's measuring the pH, gives a data table like this over here. So it's showing you initially at every change in 5 milliliters, and then it gets down to where you're just changing in 1 milliliter range, how much the pH is changing. And so you can have a beautiful graph that looks like this. And it can show you what's going on, and we can do all of our calculations that we need to do, which we're about to in just a second. All right, so when we have a weak acid and a strong base, the equivalence point represents the stoichiometric balance between your moles of your acid, which is the acetic acid, when you first started, which is down here. So you have your moles of your acid, and then the moles of the hydroxide or sodium hydroxide that you added, or the hydroxide, it's the same thing. So only for strong acids is that equivalence point at 7. Since we had a weak acid and a strong base, it's got to be greater than 7, and then the opposite would also be true. All right, oops, clicking the wrong screen. Here we go. All right, so here comes one of our first problems. So the steps on the screen are great, but I'm not going to pay too much attention to them because I'm going to come over here and do the problem. like this. Well, that one's dumb. I need the problem. Okay, so calculate the pH. Calculate the pH in the titration of 25 mils of 0.1 molar acetic acid by sodium hydroxide after the addition to the acidic solution. They word this so complicated. Of 35 mils of 0.1 NaOH. And they give us the Ka for acetic acid. All right, so I have 25 mils and 35 mils. Let's see if I can remember that. There's NaOH. Okay. See if I can remember. I may have to click back. I'm gonna write down what I got. I got 25 milliliters of 0.100 molar acetic acid. And then I have 35 mils of 0.100 molar NaOH. And I know the Ka value for the acetic acid is 1.8 times 10 to the negative 5. And there is no Kb because it's a strong base. So it doesn't have one. It's just a really big number. Okay, so I've got that. So I don't need to go back. There we go. So I got lots of space. Okay, so I'm in the situation to where I'm quickly assessing. I have a weak acid and I have a strong base. So I'm up here thinking to myself, okay, I have a strong weak scenario, one of these three. Well, I got to figure out if I have someone in excess or am I dealing with equimolar? Well, they're both 0.1 molar, right? But this is not equimolar because if you notice, they have different volumes of each. And hopefully you automatically know who you're going to have extra of because you have 35 mils of 0.1 molar NaOH instead of the 25 mils of the 0.1 molar acetic acid. So you should notice that you're going to have extra of the NaOH or extra of the OH floating around. So extra of the strong. So I am going to have extra of the strong, which is this first one here. But we'll go calculate it real quick, okay? All right, so let's go calculate it so we can confirm. Now what I'm going to do is I try to make my life easy, and you might think I'm not making your life easy by doing this, but it just makes my life so much easier. I want to, number one, know my stuff. I want to be fast on the AP exam, and I don't want to do any unnecessary and extra calculations because I run the risk of making just an error of typing something into the calculator the wrong way, an error of writing the wrong number down on the paper. There are so many ways that you can make little errors that you don't want to do that on the AP exam. So you want to minimize the amount of calculations that you do if at all possible. All of that to say, to calculate the moles, typically you would need to convert the milliliters to liters. I'm not going to do it. I'm just going to leave it as millimoles. It will all work out in the end. So if I multiply milliliters by molarity, I get millimoles. If I multiply liters times the molarity, I get moles. But I'm just gonna let this go. It's gonna be fine. All right, so I have I have 25 milliliters. I'm gonna multiply by the 0.1 molar, okay? And I get 2.5. So I have 2.5 millimoles of the acid. I'm not gonna write the acid name because I'm doing this super quick on the AP exam, right? And then here, if I have 35 milliliters times 0.1 molar, then hopefully you already know this is 3.5 millimoles of my NaOH. Okay, so what that tells me is that I have 3.5 millimoles of the base and 2.5 millimoles of the acid. So I have excess base. How much excess base do I have? Subtract them. So I have 3.5 millimoles minus the 2.5 millimoles. And when I subtract them, here we go. I have 1 millimole of excess base. which is NaOH, but I'm just going to go ahead and write the OH minus because that's what matters. The Na plus isn't doing anything right now. It's just floating around. It's the OH minus that I care about. So the 3.5 millimoles minus the 2.5 millimoles. So 2.5 millimoles went off to go make water somewhere. And most of those are going to stay intact as water. But the 1 millimole that's left over is my hydroxide ion. Okay, great. So now I have my moles. I have 1 millimole of hydroxide ion in excess. But think of what's going on. I'm solving for the pH. Keep your eye on the prize. Okay? Eye on the prize. Right? I need the concentration. In order to get to the pH, I need the concentration of the H plus, or if I get the concentration of the OH minus, I can go get the POH and still get it. So I need to find the concentration. So I have moles. I know I can find the concentration if I divide 1 millimole by the new volume. Don't forget to add them together. I have 25 milliliters of my acid and 35 milliliters of my base. So when I add them together, I have 60 milliliters. Now your millis cancel. Of my solution. And then I get 1 divided by 60. Gonna be a little number. All right, 0.016, and it's like 66666, a whole bunch of them. Well, I'll just leave it right here for right now. I'll deal with the sig figs at the end. All right, that's the molarity of my OH minus. Well, that's great. So now that's the concentration of the hydroxide ions. I can take the negative log of this number. So the negative log of 0.01667 equals, on my calculator, negative log of that answer. And I get 1.7. I'm going to go look at my sig figs right now, okay? So we're going to look at our sig figs, and if I copied everything over properly, then I'm good. If I didn't, sorry. I have 3 here, 3 here, 3 here, 3 here. Okay, Ka values don't count towards your sig figs because those are constants. I have 3 sig figs in my calculation. Remember, this is only 1 sig fig because it's a logarithmic number. So I have 1.778. So 778. And also keep in mind, when you take the negative log of that, watch out. That is not the answer. This is the POH because that's the OH minus concentration. And put the brakes on. Make sure your number makes sense. I know I said you gotta be fast, but think, if I have extra OH minus in solution, is my pH going to be less than 7? No, it should be higher than 7, right? Because it's basic. So in order for me to get the pH, it's going to be 14 minus 1.778. So that's going to be 14 minus 12.222. Okay, so 12.222, that has 3 sig figs in it. And this is the pH. Oh, cut the one off. Fix this. Okay. There we go, better. So that's the pH of my solution. So when we are dealing with a strong weak scenario, first thing you gotta do is figure out your moles, do this, and determine who's in excess. And then once you know who's in excess, you'll know what to do. You have your moles, you have your moles in excess, find the molarity, don't forget to add the volumes together, and then you have your pH. Got it. And this is your best scenario is when your strong is in, or your easiest scenario is when strong is in excess. If your weak is in excess, then you're dealing with Henderson-Hasselbalch, and then if you have no excess, then you're dealing with Rice. We're going to spend some time with Henderson-Hasselbalch later in a different section, so I won't be working one of those today. I will work one, multiples, but not today. Okay, so when we just did this NaOH, so when the weak acid is in excess, you're dealing in the buffer region, which we've already talked about. It's a Henderson-Hasselbalch equation. All right, so in this particular titration, I see that I am starting with a weak base and I'm ending with a strong acid because the pH is down below 2 at the end. I have my equivalence point here, and then I have my buffer region, and then I have my midpoint. So here's the thing. If the weak base, so right here, if the weak base is in excess, then you are in this region. And so that's the HH, the Henderson-Hasselbalch equation. You're in the buffer region. But if the strong acid is in excess, then you're talking about, you're gonna do the calculations, I can't talk. If the strong acid's in excess, then the pH is the resulting solution. You have to find out how many, like we just did, how many moles of the excess, in this case base, or acid, whoever strong is left over. So whoever strong, you have to find out how many moles they are, divide it by the volume to get their concentration, and then do your calculation to get your pH. That was hard to get out. All right, so that's what we're going to talk about. And then equimolar is the next one. This can be a little tough. All right, so for an equimolar, so if the weak base and the strong acid, or the weak acid and the strong base, whichever one you got, are equimolar, then you are at the equivalence point. You are right there. You are at that dot that's in the middle of that inflection zone. All right, so the moles of the acid equals the moles of the base. So neither one of them are in excess at that exact moment in time. So if you were to find out the moles of each one of them and subtract them, your number is 0. So that causes us a problem. And then weak, which we'll talk more about later, but a weak acid and a weak base are combined. So it's an acid-base reaction, just like any other acid base. So this is my acid, and this is my base, and then acids donate a proton. And so this is my conjugate base, and this is my conjugate acid. So they will be at equilibrium, and then you've got to know a little bit more about what's going on in order to solve. You got to have some Ka and Kb values so you can do some calculating. Okay, this is our last problem. We have 100 milliliters of 0.1000 molar acetic acid is added to 100 milliliters of 0.100 molar potassium hydroxide. Calculate the pH of the resulting solution. The Ka of acetic acid is there it is. So it looks very similar to the last problem we just worked. But it's not. Okay, so here we go. I have 100, and I think these were the sig figs, milliliters of 0.100 molar acetic acid, and I have 100 milliliters of 0.100 molar, I think it said KOH. If it said NaOH, it doesn't really matter, but I'm pretty sure that one said KOH. Then they told me that the Ka for my acid was 1.8 times 10 to the negative 5. And my goal is, what is the pH? So that means I am looking for the concentration of the H plus or the hydroxide OH minus. So eye on the prize, always stay focused on what you're trying to find out. Okay, so this starts to get a little bit tough because we're dealing with no excess, right? Because if I were to multiply these two together, I have 100 times 0.1. So 100 times 0.1 should be pretty easy. It's 10. I have 10 millimoles of my acid. And then I also have 10 millimoles of my base. So when I subtract them, neither one of them are in excess, right? So between the H plus and the OH minus, they went off to make water, and there are no H pluses or OH minuses left. So I need you to visualize what's floating around in this solution. Okay, so if you think about what's floating around in the solution, you've got some K pluses, they're not doing anything. You have some acetate, and you have water. Okay, so we know that water can auto-ionize and split, right? H plus and OH minus. Well, remember that this is a strong base, this is a weak acid, and so what that means to you is that this is a strong conjugate. Okay, the K plus is a weak conjugate. We don't care about the K, we don't care about weak. Strong wins. So strong is the winner. So I need to focus on this acetate. That's going to be my key. So what's going to happen is I need to take him separately. I'm going to take him out, and he is going to end up reacting with the water. And he's an AQ. Oops. And he's going to be weak. He will react with water. He's a strong conjugate, but he will make a weak acid. And so what I end up doing is he ends up yanking off one of these H pluses, and I get that. So why did I pick that one again? Because he's strong. He's the one that's going to be floating around in the solution and actually doing stuff and reacting with the water. Is the K going to react with the OH minus? No, because KOH is a strong base and they're going to be ionized 100% and they're not going to come together and do anything. But the acetate is going to react with some of the water, H pluses from the water, and give us back some acetic acid and some OH minus floating around the solution. And when you see this, it should tell you that you're going to have what type of solution? Basic. And does it make sense that I started with a strong base and a weak acid and I'm going to end up with a basic solution? And I hope it does, because we've already talked about that in terms of looking at the titrations. Okay, so if you look back up here at the top, if we have nothing in excess, we got to go to a rice table. Okay, so this is going back to Unit 7. We can do rice tables in our sleep, hopefully. R-I-C-E. Some of us can. All right, so here we go. What's the initial concentration of this acetate? I don't know. We got to go calculate it. Okay, well, let's take a look at it. I have 10 millimoles of H plus. That means I also have 10 millimoles of acetate. So this is moles. I don't want moles. I want concentration. So it's going to be 10 millimoles divided by my new volume, which is 200 milliliters. And the millis cancel out. So I have 10 divided by 200. And you know what? This for those of us that don't like math, 10 divided by 200 is 0.05. All right, so I have 0.05. That's my initial concentration of the acetate. So when this first reacts, that's what I've got. And then what's going to happen is then the acetate will react with the water, but initially I don't have any of this. We know that's going to cause a shift in this direction. And then I have this, this, and this. Great. So as we've already identified, this is basic. So that means I need an expression, and it needs to be Kb because it's a basic solution, not Ka, Kb. So concentration. Wrong one. Over. Don't put water in there. All right, so that's my Kb expression. All right, so now I can start plugging in, and I have in my numerator, I'm going to end up with x squared, and in my denominator, I have 0.5 minus x. Now, put the brakes on. I need this to be equal to a Kb value in order for me to solve it. However, I have the Ka value for acetate, right? So I have the Ka value for, it's right here, for the, not for acetate, for the acetic acid, if I want to know the Kb value for its conjugate, then I have to use this equation that it's been like maybe 8.1 that we talked about it. Remember this equation? That one. And the Kw is 1.0 times 10 to the negative 14. And the Ka was 1.8 times 10 to the negative 5 times the Kb. And I will talk in just a second as soon as I get my answer about why I'm doing this again. So 1 second, 10 to the negative 14. Oh, that was bad. I'm glad I caught myself. Negative 14 divided by 1.8, negative 5. All right, so I get 5.56 times 10 to the negative 10. Okay, what the heck did I just do? And where did that come from? Because a lot of kids, in my experience, can get to this. But then they either plug in the Ka and then they get it all wrong from that point, or they don't know how to get the Kb. Listen, you have the Ka for this acid, the HC2H3O2. This is his Ka value. If you want to know his conjugate's Kb value, then you plug into this equation, because I have water and I have its acid and its conjugate base. So I can do my calculations and find the Kb value for the acetate ion, which happens to be, where did my pen go? Here it is. 5.56 times 10 to the negative 10. Okay, I can neglect this plus or minus x, get rid of it. Let's do some math. All right, I'm going to times that by 0.5. And I'm going to take the square root of it. All right, so I have x equals 1.667 times 10 to the negative 5. All right, make sure I've got all my stuff in here correctly. 5.6 times to the negative 10 times 0.5. Oh, it's not 0.5, it's 0.05. I need to be in class so you guys can catch me when I make a mistake. 0.05. Now take the square root of that answer. Okay, so that's different. 5.27 times 10 to the negative 6. That's what x is. All right, let me double check. 5.56 times 10 to the negative 10 times 0.05. And take the square root. And I have 5.27 times 10 to the negative 6. All right, that's what I got. All right, so that is my x value, and my x is the concentration of my OH minus. Well, let's take the negative log of that. So negative log of that answer, and I get that the POH is 5.2779. 8. Way too many digits, but that's okay. And the pH is equal to 14 minus that number. So 14 minus that answer, and I get my pH is equal to 8 let's check our sig figs. I have 4 and 4 and 3 and 3, so we're gonna have 3 sig figs. So 8.722. Okay, now stop for a second and let's see if that makes sense. 8.722, that's basic, right? So this is a reaction between a weak acid and a strong base. Should the pH at the equivalence point, not the final, at the ending, but at the equivalence point, should it be a little bit basic, like above 7? Yes, it should be. And it's probably not going to be up there like 12. It's just going to be a little bit higher. So somewhere like between 8 and 9, just depends on, you know, who you're working with. But that sounds very plausible. That's a possibly the right answer. Okay, so I know this is a lot, and I know there's a lot of information going on here. But I want you to absorb that, think about it, and work through some of the problems, okay? All right, I'll talk to you guys later.